So this is lecture 2 of Igneous Petrology course. So we will start with binary albite anorthite system. It is also known as binary solid solution system. So in this, as this name binary is here, binary means there will be two components here. There will be two components in the system. So this is a solid solution, means both the phases will coexist together and it will form a solid solution. There will be no two different separate phase. Both the components will combine, both the phases will combine, and it will form a one solid solution. So there will be a intermediate minerals between albite and anorthite. So here it is a two or more solids can combine in an arbitrary amount forming a single phase. So this is important. These two solids will combine to form a single phase. We will see in the graph also. Now here the albite will change into the anorthite by the process of coupled substitution. By coupled substitution. What coupled substitution is? So in coupled substitution, what happens? Suppose you have a albite. The formula is NaLSi3O8 and anorthite is CaAl2Si2O8. So if you break down, this will become half of Na2O, 3 SiO2 and half of Al2O3, and in anorthite that is CaAl2Si2O8. So it will be CaO, Al2O3 and twice of SiO2. So here one of the SiO2 will get replaced. So if you see here was 3 SiO2, so one SiO2 will get replaced. If you go on that side, Al2O3 will also be replaced, and this half of the Na2O is replaced by CaO. So this entire process here is known as coupled substitution, and this question came in GATE 2023, that which of the following group of minerals shows coupled substitution. So this was the answer for that, that is albite and anorthite. Albite and anorthite shows coupled substitution. And what coupled substitution is? In this, one SiO2 is replaced, half Na2 is replaced by CO, and this one SiO2 it will replace half of the Al2O3. So this is together is known as coupled substitution. So it is a solid solution. Intermediate composition exists and the same crystal structure may form. So intermediate composition structure will coexist together in this. This is in plagioclase feldspar. So if you have seen the diagram of plagioclase feldspar, it is like this. So here was orthoclase, here was albite, and here was anorthite. So in between this, from here to here, a different solid will coexist. So they combine this from here to here, they combine will form a solid solution. So here we will see that different compound like oligoclase, andesine, labradorite, bentonite and anorthite will be there. So these are the intermediate composition between this and this solid solution. Now after this we will see this binary graph here. So here in this y-axis represent the temperature and x-axis represent the composition. So if the bulk composition is at point A, if we crystallize this phase is entire liquid, okay, this phase is entire liquid and here is the complete solid. So if we crystallize from here to here, this A is a bulk composition, and if we crystallize A from here, when it hits the liquidus, so the composition we will measure by projecting this on this side like this. So this is the place where first solid form. This is the place where first solid form, and if we extend this line in the x-axis, we can measure the composition of the first solid. So this will represent the composition of the first solid. Now if we further crystallize this, like this, it will hit this position, and here if this is the equilibrium melting, if this is the equilibrium melting, the composition will be same as the bulk composition. So if it is a equilibrium melting, the composition will be same as bulk composition. This is a case for equilibrium crystallization. This is a case for equilibrium crystallization. Now suppose if someone asks that what is the composition of solid or liquid at this point, then we will apply a lever rule here. Then what we will do, we will apply a lever rule here. We will project like this, and this distance, let's say, is DE, and this distance is EF. So if we have to calculate the percentage of melt, for example, percentage of melt, we will take the opposite side where solid is, means we will select the right side here, because here is the solid, so it will be EF by total, that is DE plus EF. So this is percentage of solid. If we have to calculate percentage of melt, if we have to calculate the percentage of solid, then we will take the opposite side, that is DE, this one, by DE plus EF total. So what we have to understand here is, if it is a case of equilibrium crystallization, the initial composition will be same as the bulk composition. Now if we want to calculate the degree of freedom, let's say at this point x, so what is the formula for degree of freedom? F is equal to C minus 5 plus 2. So here in case of igneous rock, we consider this as 1 here, okay, because it is a isobaric process, so we consider here +1. We consider pressure as constant, so we use only one invariant case here. So number of component, as it is a binary component, we will always take as 2, and number of phases here is only one phase, that is liquid, -1 plus 1. So degree of freedom will come out to be 2 at this point here at x. Now if someone asks to calculate degree of freedom at point B, so at point B, number of components at point B, number of components will be again your 2, as it is a binary component system, and number of phases will be this liquid and solid, both the phases are there, so 2 plus 1, so degree of freedom will be 1 here. Similarly, you can calculate degree of freedom here also, it will come out to be 2 because only one phase is there. At this point degree of freedom will become again 1, and again degree of freedom will be 2 here. So now what will happen, now this I will use purple color here. Now I will explain the entire process. Here is the bulk composition at A, it start to crystallize. This is the composition of our first solid. Now this curve will move in this direction like this, the another composition will be this one, then further this graph will move like this, and the composition of solid will be this purple color. I am showing the composition of solid here like this. This is a case of equilibrium crystallization. Now when this curve reach here, the last melt composition will be there. Why? Because here the composition of solid is similar to composition of the melt. So this is the our composition of last solid. Okay, this will be a composition of last. This is a composition of first solid. this will be the composition of final solid in case of equilibrium crystallization. So this is how we will solve this. Now let's say we'll see the reaction here now. Now the starting temperature is 1500 degrees Celsius, as you can see in the figure. This is our starting temperature, which is at 1550 degrees Celsius, and the bulk composition here is 60% anorthite and 40% albite. Means the bulk composition of the melt here, this one is, you can see from here, it is 60% anorthite and 40% albite. Now as this reaction proceeds, okay, now as this reaction proceeds, I will little bit clear this thing. Now see, this is the bulk composition. Now as this our curve will hit the liquidus, the first crystal will start to crystallize. So the reaction here, then reaction here will be liquid 1, this is our liquid, will give one solid 1, and the composition of this liquid will change because it has given the solid 1, so it will become liquid 2, and this curve will move in this direction. So another composition we will get of this one, as I have discussed before. Now further this will move here like this, another composition will be of this one, and the last composition will be like this, which is equivalent to your bulk composition. So this I have written here. So liquid 1 plus solid 1 will give liquid 2 plus solid 2 if the reaction further proceeds. Means from here to here it is telling that our liquid 1 here plus solid 1 which earlier formed will give liquid 2 plus solid 2. So this is a continuous reaction. Now this is a lever rule, how we will apply the lever rule, which I have explained before also. Now suppose this is our bulk composition like this. Now we will draw a tie line like this, and if you want to calculate the percentage of melt, so we will take the opposite side, because here left hand side is the melt and here will be the solid. So to calculate the melt, we will take the solid side, that is BC. So here BC will be there, divided by total into 100. To calculate the percentage of solid, we will take the opposite side, that is this one AB, by total AC into 100. After this we will see what fractional crystallization is. Fractional crystallization means whatever melt which is forming, we are removing that melt. Okay, whatever melt is forming, we are removing that melt. So if we see this, now this is our initial composition at A. As I told, it will hit the liquidus curve and first solid is formed, and this solid is removed. So the first solid which was formed here, as we have seen, it was 60% anorthite and 40% albite. So first solid which was formed will be rich in anorthite, and you are removing that, right? You are removing the first solid which is rich in anorthite, so obviously the composition of the anorthite in the melt will tend to decrease. So as the composition of the anorthite in the melt is tending to decrease, the curve will shift towards more albitic side. So whatever melt which was formed here, which was of composition, this one, this was the composition of solid which was formed. Let's say it is 90% albite anorthite and 10% albite, and I am removing this thing. Okay, this composition of solid is removed. Now the curve will move toward this side, and this composition of the solid is formed, and this is also removed from the system. Again this will curve will go in this direction, and this bulk composition thing will form, and this will also removed from the system. So curve will move more towards the albetic end like this, and the final melt which we get, okay, final composition will be very albetic rich. Okay, so reaction will not stop, and it will reach to the albite. This I have written. So the final melt and solid is of composition of pure albite. So fractional crystallization and partial melting means whatever melt is formed, if you go in opposite direction, means if I go in opposite direction, like if my bulk composition is here, for example, so this is my first melt which is forming, so I will look on this side. So this is a composition of the first melt. So if this is removed, okay, then this is known as partial melting. Okay, so is an important process. They cause significant change in the final rock composition that crystallize beginning with the same source rock. Now where this process operates, it we can see it operates in the magma chamber, like as you can see in this figure. This is our magma chamber is here. Now let's say this is a plagioclase rich magma. Now whatever early crystal which forms will settle down here, and because of this settling they will lose contact with the magma. So if suppose here is the magma, so these crystals which formed here, these crystals which formed here will lose its contact from the magma. Okay, so here you can see the fractional crystallization process is happening because whatever crystal which is forming is not in contact with the magma now. So this I have written here. This in fractional crystallization will result in solid, and this solid is removed from the system. Now we will see the partial melting. In partial melting, my melt is removed. Okay, in case of fractional crystallization, solid was getting removed. In case of partial melting, the melt will be removed. So it is happened by two process. First one is by relic fractionation, and another one is by batch melting. So in batch melting, what happens, whenever I heat a rock, suppose this is a rock here, and you are providing the heat here. So suppose let's say melt is generated. Let's say this melt is generated around this, like this. So this melt will remain in contact with the rock for some time, and more melt will generate like this up to certain point. After this entire melt is removed. After accumulation of certain amount of melt, this entire melt is removed. Means your melt is removed in batches. Okay, our melt is removed in batches. So this is what, this is our melt. So this is written here, melt is removed after certain amount is accumulated, like I have explained here. So this is the melt which is accumulated on the outer side, and certain amount of melt should be accumulated before it is removed. Now if you see in this example here, okay, let's say this is our initial composition, okay, bulk composition here. Now I have started to melt this rock, and this is the initial composition, and this melt which formed in the bulk is removed. So this will shift on this side. means this graph will shift on this side, so that will be the next composition here. Okay, wait, I will explain this again. So here is my bulk composition X of solid, and it started to melt. So this was our composition of melt here. This melt is removed as I have written here. Now this graph will move toward more anorthite side. So this will be the another composition of the melt. Now this melt is removed. So you can see here that this portion your melt is getting accumulated. Okay, your melt is removed in the batches. So final liquid will be more anorthite rich. As you can see, this graph is moving toward the anorthite in case of both. Okay, in case of both relic fractionation, batch melting. So batch melting I have explained. Now we will move to the relic fractionation part. In relic fractionation, what happens, your melt will be in contact with the solid, it will not removed in the batches. Okay, means whenever your melt is formed, like suppose this is your rock, and as soon as the melt form, this is residual solid, as soon as the melt form, it will get detached from the system as soon as the melt form. So here in this I have explained the example of batch melting here. Now you can see here how it is formed in the batches. From here to here one batch is there, from here to here one batch is there. So this is the composition of the melt. Now this olivine system is similar to albite anorthite system. So it is between the uh, phyllite and forsterite, and there will be solid solution between this. So here I have explained the binary eutectic system. The lecture 2, in the lecture 3 we will see the eutectic system. I hope this video will be helpful. Thank you.